To understand how heat jumps between objects, we have to start with a perfect thermal sponge. In thermodynamics, we call this a black surface, or a black body. It absorbs every single drop of incoming heat radiation and reflects absolutely nothing back, before eventually glowing to emit its own heat. Compare that to a shiny surface, which bounces energy away before it can be absorbed. Because a perfect black body doesn't reflect any energy, calculating the heat transfer is incredibly straightforward. We only need to figure out exactly how much heat the surface directly emits on its own. This graphic shows the exact relationship. Look at the bottom equation. This calculates the net radiation heat transfer, represented by Q dot, moving between two black surfaces. The math breaks down into three clear parts. First, the area, A1, how large the emitting surface is. Second, the view factor, F, a physical measurement of how much of surface 2 is actually visible from surface 1. And finally, the temperature of both surfaces, raised to the fourth power. Consider what happens if a surface is curved, like the inside of a bowl. Even if one part of the surface radiates heat toward another part of itself, the temperatures are uniform. Every watt of energy sent is balanced by a watt received from the other side. This is why the net heat transfer from a surface to itself is always zero, regardless of how complex its shape might be. But actual engineering problems rarely deal with perfect black bodies. Real surfaces reflect heat. Suddenly, the math gets complicated because you have to track both the heat a material emits and the heat it bounces around a room. To solve this, we use a concept called radiosity, represented by J. Radiosity is the total radiation leaving a surface. It combines the surface's internal emissive power with the external incoming heat it reflects, merging them into one unified value. If we map this back to our perfect black body, which has zero reflection, radiosity perfectly equals emissive power. Look at the structure of our heat equations. We have a flow, Q dot, determined by a difference in potential, divided by a resistance. This mathematical architecture is identical to Ohm's law for electricity. By treating emissive power as voltage and heat flow as current, we can map entire radiation enclosures into simple electrical networks. Look at figure 13-21 on the right. This shows our first thermal roadblock, surface resistance. This node, stretching from emissive power to radiosity, measures how difficult it is for heat to actually escape the material's surface, which is dictated by the material's emissivity. Once heat escapes the surface, it hits the second roadblock, shown in this formula, space resistance. This deals strictly with geometry. It calculates how hard it is for heat to travel across the gap between two surfaces, driven largely by the view factor. In an enclosed space with multiple surfaces, we apply the conservation of energy. As shown in figure 13-23, the total heat leaving surface I is simply the sum of the distinct heat pathways branching out to all the other individual surfaces in that space. As you calculate these pathways, pay attention to the math. A positive heat transfer value means net heat is leaving the surface. If your calculation yields a negative value, it means the surface is actually gaining radiation energy. Let's put this into practice. Grab a piece of paper and pause the video. Try to draw the electrical circuit linking two facing parallel disks, starting from surface 1's emissive power and ending at surface 2's emissive power. In figure 13-24, three resistors link node EB1 to EB2. Heat travels through disk 1's surface resistance, crosses the space resistance, and pushes through disk 2's surface resistance. We calculate total heat transfer by adding all three values to form one unified denominator. Let's consolidate. Here is your cheat sheet. Black bodies perfectly absorb and emit, with zero reflection. We map thermal problems to electrical circuits using Ohm's law. Total resistance combines surface and space resistance. Finally, a negative heat transfer value means energy is gained. By mapping messy, real-world thermodynamic reflections into a structured network, we can determine the heat flow between any number of surfaces using a systematic circuit analysis.